side. So this thing is going to rotate one way or the other, right? Some magnets, some motors, by the way, can spin equally well either way. And I'm not exactly sure what makes it prefer one way or the other. But it's going to spin around and try to get this north pole close to that south pole, yes? Well, as soon as it gets there, it's almost getting there, right? A very sad thing happens. There's a little switch up here that switches the polarity. So just as it's going, yay, I'm here at last, the North Pole is arriving near the South Pole, and we can live happily ever after, right? This is so tragic, right? This switch switches the polarity so that it's unhappy again, right? And it races again to the other side. As soon as it gets to the other side, it switches again, right? And it switches and it switches and it switches, and it's always switching it so that there's always a torque spinning it this way. Isn't that wild? Isn't that mean? It's mean to that magnet. And the thing that does that is called a commutator, which is a physics word that means at both times communist and dictator. Okay? Which is just really bad. It's kind of a mean thing, right? Okay? So let me turn this thing on. Let me turn up the current here, and let me see if we can. Which way does it want to spin? There we go. A little applause there. You can see. I don't know if you can see it where you are, but where that metal touches the commutator, there's sparks jumping there, because it's not a trivial thing to make a magnet have the current flow one way and then suddenly reverse. Okay? I don't know if you've noticed it, but when you like unplug your vacuum cleaner when it's running, you get a big spark. Yeah. Right? That's because you're making basically a magnetic field in that motor collapse really quickly, which we don't know this yet, but that makes induces a very large voltage. Okay? Actually, we sort of do know that, right? Anyway, so this is a very bad motor that's easy to understand, okay? But the problem with this is that if you looked at the velocity of that thing, the velocity would be varying 2 times a cycle. It would have a very large torque, then a smaller torque, then a large torque and a smaller torque, right? This is not very good if you're trying to make a disk drive spin at a uniform rate, okay? So if you're trying to spin this guy at a very uniform rate and read data off it at a uniform rate, that's not your motor to use. Besides the fact that it's much too large and would only last for about 15 minutes and then it would burn out, right? Those would also be drawbacks. So what you want is you want to make a motor that has more poles in it. Okay, can I get this guy out of there? Here it is. Pull it out. Look inside there. How many poles do you see? I believe there's 12 poles in there. Okay? Isn't that crazy? On this thing, this little hub that fits down in there, probably, I don't know exactly what's going on there. We could mess with it. But it might have north, south, north, south, north, south, north, south, right? Okay. Now, to be sure, these things are not switching on and off like that. There's no sparks flying. That would, like, destroy a hard drive. It would not be a good thing, right? And so there's some sort of you can see the circuitry going in there, and I've taken the circuit boards off there. But to be sure, this is one of the smoothest motors you're ever going to see. There's almost no fluctuation of fast, slow, fast, slow, fast, slow, because it's got so many poles, and to be sure, it's taking the voltage and carefully massaging it just right so that it's going to spin around at a uniform rate, right? So we can pass that around. You got to pull the magnet out of there. It doesn't want to be pulled out of there because it likes that spot. And you can look in there. Here's the permanent magnet. Those are the poles, and you ought to be able to, by manipulating that magnetic field, make this thing spin, which is what's going on there. Okay. And then a speaker is a very simple device. Looks very complex, but basically you've got, in the speaker, you've got wires that are flowing this way. It's hard to see in this drawing, but there's supposed to be a coil of wires. And so this speaker, basically this cone has a magnet on it, yes? It is up against another permanent magnet, okay? And when the current is flowing from your stereo in such a way that it makes this magnet repel this magnet, the speaker excurts, yeah? In other words, it goes out, it goes on an excursion, yeah? Okay, so the speaker gets pushed out, and when you reverse the current and make this magnet attract this magnet, the speaker incurts, which is not a word, but it should be. Okay, it goes in, right? And so if you take the speaker and you put the voltage one way, it goes out, and you put the voltage the other way, and it goes in. It gets pulled in, right? And so I've got a couple things to pass around. Yes, sir, question?
What would make, like, the speaker make really horrible noises?
Horrible noises. Oh yeah, well, if you send a bad signal in, it can make a horrible noise, right? So if you've got some distortion along there, right? The other thing that can make a horrible noise is that you blow the speaker out. There's little springs here on the edge that allow it to move in and out. And if you rip those springs, then the speaker just sits there and hits solid objects, which makes it make a really nasty noise, right? I'll pass this around. This is a speaker, and somebody's taken the magnets off the back so that you can see. And what I want you to see is, first off, that there's in there is a coil. There's a coil of wire, a finely wound coil of wire. It's very lightweight. When you make the coil for a speaker, it's called the voice coil, you've got a trade-off. If you make that coil heavy enough to handle a lot of power, it's heavy physically. It's got a lot of inertia, and so it can't move very fast, right? And so drivers, enormous subwoofers, have very heavy wires, but they move slowly. They move at low frequencies, right? Okay. Smaller speakers can't handle as much power, so they're lighter, right? And they have less inertia. They can move faster, right? This thing's somewhere in the middle. It's just not really a very good speaker at all. What's missing from here are these big ceramic magnets, and they're missing because I took them off because I wanted to use them for something, right? And I think I've got one more show and tell thing to pass around. All right. Here's the other thing that I would I'm sorry, have you take a look at. All I did was I grabbed a speaker. This is a computer speaker from the back, and what you want to do is just take these alligator clips and attach one side to the negative side, one side to the positive side. Okay? If you do it one way, the way I'm doing it right now, the speaker is inverting. Flip it around, right? Notice that the speaker should excurt. And of course, your stereo is just sending a signal that's, right? Sound is just compression and decompression of air. And so that's how we turn it into sound. So we can pass this guy around. Please be very nice to my speaker. They're very delicate things. Don't poke things through it. And it turns out that worn out AA batteries are very good on speakers. Something that I would warn you about with your own speakers is that one good way to destroy a speaker is to send a direct current through them. Okay? I'm sending around a 1.5 volt battery. It's not going to fry that speaker, but you can fry a speaker real fast with direct current. Okay? So just be careful. They're good at vibrating back and forth, not so good at being pushed all the way out and held there, right? And then also they can resist. They've got more resistance when the voltage is changing. There we go. Okay. Yes. Is that enough? That's enough of that stuff, isn't it? Yeah. Show and tell.